Welcome back to Calculus 2. Today we're going to look at comparison tests, a few more tests for convergence or divergence of series. First one we're going to look at is what's just called the comparison or direct comparison test. It's a lot like the direct comparison test for integrals, in that the idea is if you have these series, if you can bound a series above by a finite series, at least on the tail, at least after some finite number, it's always bounded. Then, if the upper bound converges, so does the lower bound. Similarly, if you can bound the terms of a series below by the terms of another series, and the lower series diverges, so must the higher series. So it'll push it either way. If you have a convergent series bounding your series from above, it will mean your series is convergent. If you have a divergent series bounding your series from below, your series is divergent. I'm not actually going to present the proof. It is in the textbook if you would like to see it. Let's go ahead and do some examples. So let's start off with this one. This is a pretty classic case of we have a rational expression in our series here. And rational expressions, it's usually a good idea to think of them as p-series. So, for example, this is going to behave very similarly to 1 over n. Now let's see if we can actually bound it that way. 1 over n diverges, so if I would want to do a bounding operation and use the direct comparison test, I'd want to bound it from below. So let's see, if I replace the top with 1, I'm making the top smaller. So that would actually be a problem. But let's actually do this. If we make the bottom smaller, if we make the bottom bigger, that'll make the fraction smaller. And if we look at this, this is 1 over 2n plus 1 over n, 2n squared. This divergent p-series this convergent p-series, and if you remember back in our introduction to series videos, we actually presented a properties of series which mentioned the sum of a convergent and divergent series is divergent. So this is divergent. So is this by direct comparison test. Let's do another one. That's probably not the only thing you could come up with, but that works well enough. I basically just made the denominator larger by replacing that n with plus n squared. I think that's a geometric series, if I recall. Yeah. That would converge. So I think this will as well. Because if I do that... Well, no. I'd want to bound it from above. Let's see here. If I want to bound it from above, I want to make the denominator smaller. So that is less than or equal to 1 over n times n, which is n times n, which is 1 over n squared. And yeah, 1 over n squared is a convergent p-series. Let's see. I made the denominator smaller, because, yeah, for 1 to infinity, 3 to the n is going to be bigger than n. So I replaced 3 to the n with n. I made the denominator smaller, which makes the fraction bigger. Yeah. You have to be careful when you do that kind of thing. It's easy to get confused because of the opposites, you know. When you make a bottom of a fraction bigger, you make the fraction smaller. When you make the top bigger, you make the fraction bigger. It's easy to lose track of which way you're going. Yeah, like if I plugged in 2, this would be 1 over 4, whereas this would be 1 over 2 times 9, so 1 over 18. And 1 over 18 is definitely less than 1 over 4. So yeah, convergent p-series converges by direct comparison test. And you can, a lot of these times you can kind of give yourself an idea of which way to go, just because this is, you know, 3 to the n increases a lot more quickly than n, so you can think, well, this will basically behave like 1 over 3 to the n, which I suppose I could have also done it that way. Yeah, I could have also bounded by 1 over 3 to the n, and that is a convergent geometric series. Because, like we talked about in, I believe this is our first video on series, if the r, which in this case is 1/3, is less than 1 in absolute value, the geometric series must converge, and it actually would converge to a over 1 minus r, which in that case would be 1 over 1 minus 1/3. But with the n there, you know, that'll affect the sum, so I'm not going to find the sum. I think that's all we're going to do for just direct comparison tests. I think we're going to look at the next test now. We'll come back to the direct comparison test. The last set of problems will be use whatever test you can, so we'll get back to it. For right now, let's talk about the limit comparison test. Again, very similar to the limit comparison test for integrals. It shouldn't be that much of a surprise that a lot of the work involved with doing series and integrals is similar. Because if you remember, when we set up integrals were just the limit of an infinite sum. Integrals just came out to be an infinite sum, so in a sense, an integral is a series. So anyway, for this we have to have non-negative series. Oh, actually, it have to be uniformly positive series. I think if they were both negative, it would be okay as well, because we could basically factor out the negative. This is the main test here. If you take the limit as n goes to infinity of the terms over each other, and you get a finite value, basically they increase or decrease at the same rate, then they both have to have the same convergence or divergence. So they both converge or they both diverge. Now, these other two cases are basically just what happens if it goes to 0, so one's increasing more quickly than the other. Well, if it goes to 0, but the bottom still converges, so the bottom increases more quickly than the top, but the bottom still converges, well, that means the top has to converge as well, because the top's not going to infinity if the bottom outgrew it and was convergent. And similarly, if it goes to infinity and the bottom diverges, well, that would only happen if the top must go to infinity more quickly. So, if the bottom diverges, the top has to as well, if it goes to infinity. So it's just a few extra refinements to it. In case you don't get a perfect comparison, you know, it gets you, oh, they behave exactly like each other. If you still have something that's close, it'll basically kind of give you the cases of the direct comparison test. So let's use the limit comparison test. What do you expect this series to behave like? Well, if you think about it just as the highest powers on the rational function, that's 1 over n, but 1 over n square rooted, which is different than 1 over n. So 1 over square root n. That, I basically did this. That is a divergent p-series, because that's 1 over n to the 1/2. And remember that p-series diverge for p less than or equal to 1. So that'll diverge. If you don't believe it, you can do the integral test. So then, let's compare. So I got square root n plus 1 over n squared plus 1 over 1 over square root n. We want to take the limit as n goes to infinity. Well, that is the limit as n goes to infinity of the square root of n times the square root of n plus 1 over n squared plus 1. Which is, I'm going to multiply this in and take the limit inside the root. Square root of the limit as n goes to infinity of n squared plus n over n squared plus 1. And that's just going to go to 1. Square root of 1. So that is a constant greater than 0. So they both diverge by the limit comparison test, or the LCT. Limit comparison is pretty nice if it's obvious it's going to behave like a certain type of function, like rational expression generally perform just as if they had their leading terms on top and bottom. And here's another one that's pretty simple to do. You can tell then the 3 basically doesn't matter. We're going to compare this with 2 to the n over 4 to the n, which is 1 over 2 to the n. So if we do that division, 2 to the n over 4 to the n plus 3, it doesn't really matter whether you put your new one on the bottom or the top. Flip and multiply, you'll get 4 to the n over 4 to the n plus 3. And once again, this will go to 1. So they do have the same convergence or divergence. I didn't actually indicate what this will be, though. Let's see, that is not a p-series because it's not 1 over n. If it were 1 over n squared, it would be a p-series. This is a geometric series. And because its common ratio is less than 1, convergent. Convergent by LCT. Let's just do some generic ones. Converge or diverge any test. So we can use the integral test, we can use the nth term test for divergence, we can use the comparison test. Let's see here. Just based on this, 2 to the n over n times 2 to the n. These are very different series, so let's actually break them up. 2 to the n over n times 2 to the n. Just because it'll be simpler to compare. Minus n over n times 2 to the n. That will get me 1 over n, which is a divergent p-series. Minus 1 over 2 to the n, which is a convergent geometric series. So, because of our theorem that said if you add or subtract a convergent and divergent series, the sum or difference must diverge. There we go. Sum the difference of convergent and divergent series is divergent. It's like adding infinity in a finite number, or subtracting a finite number. You're not going to stop it from going infinite by subtracting a finite number. Alright, this is a factorial on top and bottom. And a trick when you have factorials on top and bottom as factors is that a factorial contains every factorial beneath it. So like the bottom there is n plus 2 times n plus 1 times n times n minus 1 factorial. And since I had n minus 1 factorial on the top, you can just reduce that part. So this becomes this series, n equal 1 up to infinity, of 1 over n plus 2, n plus 1 times n. And this is a very simple rational expression. It's a lot like, well, the natural thing to compare it with would be 1 over n cubed, which, since I made the denominator smaller, the fraction will be bigger. So you can either use the direct comparison test, or you can use the limit comparison test. I think I'll use the direct comparison test on this one. Yeah, I subtracted things off the bottom, so I made the bottom smaller. That means the whole fraction is bigger. This is a convergent p-series. So convergent by direct comparison test. And sometimes you might want to compare with something other than a p-series or a geometric series. They're just functions that are easy to determine the convergence or divergence. Sometimes you might have to bound by a function that you do another test on that function to show its convergence or divergence, like using the integral test, because the integral test is pretty easy. Just depends on what you're looking at. We'll get more and more complicated series as we go. Alright, here's a fun one. This relies on you knowing some formulas from much earlier in the text. When we first introduced integrals, which in our current textbook is chapter 5, but wherever that is in your current textbook, you talk about series a lot, and to evaluate some integrals without using the integral formulas, you just use sums. And to do those sums, you learn these formulas. K equal 1 up to n of k. So 1 plus 2 plus 3 plus 4 plus all the way up to k is just, all the way up to n, I should say, is just n times n plus 1 over 2. There's a formula for that. It actually comes from Gauss. So n times n plus 1 over 2. It's a neat summation formula. If you ever want to talk about how Gauss came up with it, I'll show you his thought process. It's pretty neat. But if we look at k equal 1 up to n of k squared, there's actually a formula for that too. And note that's what we have on the bottom. This would be n times n plus 1 times 2n plus 1 over 6. There's also one for cubes. K equal 1 up to n of k cubed is the n times n plus 1 over 2 squared. So let's look here. On the bottom we have the sum of squares. Well, that's easy then. That's 1 over n times n plus 1 times 2n plus 1 over 6. So we just reformulate this as sum n equal 1 to infinity of 6 over n times n plus 1 times 2n plus 1. It's just a neat little trick. Then this becomes pretty simple because you can compare it with just 6 over 2n squared. 2n cubed, I should say. Which should be 3 over n cubed. And I believe it would work that way. Yep, made the denominator smaller. Says it becomes n times 2n. Yeah. Which, and this is a convergent p-series. So, converges by direct comparison test. You could also use the limit comparison test on this one with even the same function. Or honestly, I would if I were doing limit comparison test, I would probably just use 1 over n cubed, not bother with the 3. The 3 is mainly just so I maintain the less than greater than relationship without any trouble. And that should finish the section. Next time, we'll talk about the ratio and root tests, which are tests for absolute convergence. Absolute convergence basically is if you take the absolute value of every term of the series, so basically make it positive, will it converge then? Absolute convergence does imply regular convergence, but we'll see that when we get there. Have a great day.